Let us consider a home setup where the music is audible from the adjacent room. How can we hear sound when we cannot see the sound player? This is because the sound waves bend around the corners to reach our ears. This phenomenon of bending of waves around an obstacle in their path is known as diffraction. All types of waves exhibit this phenomenon. Observe the diffraction of water waves at a narrow slit placed on its path. When the size of the slit is large, the diffraction of water waves is quite negligible. On the other hand, when the size of the slit is very small, we observe the diffraction of water waves very clearly. The diffraction of waves depends on its wavelengths. If the size of the obstacle or the slit is of the order of the wavelength of incident waves, then diffraction occurs. This condition is also applicable to light waves. The wavelength of visible light is in the range of 400 to 800 nanometer. Since the wavelength of visible light is much smaller than the dimensions of most of the obstacles it encounters, we usually do not observe any diffraction. If a screen is placed behind an opaque object, light from the point source travels in a straight line and forms a shadow on the screen. But if we look at the shadow closely, we observe that no sharp boundary exists between the shadowed and the illuminated regions. The illuminated region above the shadow of the object contains alternate bright and dark fringes because of diffraction of light, and the pattern is called diffraction pattern. Let us now study diffraction of light at a narrow slit. Place a monochromatic light source on one side and a screen on the other side of a narrow slit. When the slit is illuminated by monochromatic light, a diffraction pattern is formed on the screen. The diffraction pattern consists of a central bright band, which may be much broader than the width of the slit, with alternate dark and bright bands on both sides. The intensity of the fringes decreases very rapidly. Let us now analyze the diffraction pattern mathematically. We represent light as a beam of rays. Let the width of the slit, Ln, be A. Let the source of monochromatic light and the screen be very far away from the slit. If the source is at a faraway distance, we can regard the incident light as plane wavefronts, or alternatively, the incident rays are parallel. When a plane wavefront is incident on the slit, all the points of the plane wavefront are in phase. According to Huygens' principle, every point on the wavefront acts as a source of secondary wavelets that spread out in all directions with a speed equal to the speed of propagation of the wave. Consequently, we find so many microscopic point sources of light between L and N, which produce secondary wavelets. The diffraction fringes formed on the screen are due to the interference of these secondary wavelets produced by a large number of point sources. Since the screen is at a faraway distance, we can regard the rays as parallel. The diffraction formed in such conditions is known as Fraunhofer diffraction. Consider an arbitrary point P on the screen. Let us examine the conditions for point P to be a diffraction maxima or a diffraction minima. Let M be the midpoint of the slit and a straight line passing through M be perpendicular to the plane of the slit, which meets the screen at C. Let the line joining the points M and P make an angle theta with the normal MC. Consider light rays from 2 point sources L and N separated by a distance A reach the point P. The path difference between these rays NP minus LP is equal to NQ. From triangle LNQ, NQ is equal to A sin theta. But for small angles of theta, sin theta is approximately equal to theta. Therefore, the path difference is equal to A theta. Now we shall analyze how contributions from a large number of sources produce diffraction fringes on the screen. Let us first consider the central point C. From the figure, we can see that angle theta is 0 for point C. That means waves from all the point sources reach C in phase, and hence all path differences are also 0. Which means waves from all parts of the slit contribute in phase at C. They interfere constructively and produce maximum intensity at C. Now consider another point C1 on the screen, such that A by 2 into theta is equal to plus or minus lambda by 2. Let this be equation 1. Imagine that the slit is divided into two equal halves, LM and MN, with a width of A by 2 each. Consider the waves from the point sources located at L and M reaching the point C1. Since these two sources are separated by A by 2, the path difference between them at the point C1 is equal to A by 2 theta. Let this be equation 2. From equations 1 and 2, we can conclude that the path difference between L and M at C1 is 1/2 of the wavelength of the incident light. Hence, the waves from L and M are out of phase and interfere destructively at C1. Now, if both the half slits LM and MN are considered for every wave passing through LM, there is a corresponding wave passing through MN originating at a point A by 2 below the first one, such that the two waves are out of phase at C1. Hence, every wave arriving at C1 from the upper half of the slit LM interferes destructively with the one coming from the bottom half of the slit MN. The intensity at C1 is therefore 0, and C1 corresponds to the first minimum of the diffraction pattern. Hence, the condition for the first minima is theta is equal to plus or minus lambda by A. Let this be equation 3. Equation 3 implies that the central maxima can be made wider by making the slit narrower. We can also divide the screen into 4 parts, 6 parts, and so on. And using a similar argument, we can show that the subsequent diffraction minima occur whenever theta is equal to plus or minus 2 lambda by A, plus or minus 3 lambda by A, and so on. So, the general condition for a diffraction minima can be written as theta is equal to n lambda by A, where n is an integer. Let this be equation 4. In between two successive minima, we will have secondary maxima. We can find the location of the secondary maxima for values of theta approximately equal to n plus half into lambda by A. Let this be equation 5. Let us now verify the validity of equation 5. Imagine that the screen is split into 3 equal parts of width A by 3. Consider a point C0 approximately between C1 and C2 at an angle theta equal to 3 lambda by 2A. Now consider 2 waves from the ends of the 2 top parts. Since the width of each part of the slit is A by 3, the path difference between them at C0 is equal to A by 3 into theta, which in turn is equal to lambda by 2. Hence, these 2 waves interfere destructively at C0. In the same way, all the waves from the first part can interfere destructively with corresponding waves from the second part of the slit. Only the remaining 1/3 of the slit contributes to the intensity at C0. Therefore, the intensity of the secondary maxima is much weaker than the intensities of the central maxima. The intensity distribution due to diffraction of light is as shown. So far, we assumed that the source and the screen are placed far away from the slit. In such cases, the intensity of the fringes on the screen is less. If a converging lens is placed after the slit and the screen is placed at the focal point of the lens, then the parallel rays from the slit converge onto the screen to give a bright diffraction pattern. Note that the lens do not create any extra path difference in a parallel beam of light. A wave traveling through a distance delta x in a medium of refractive index n suffers the same phase change as when it travels a distance n delta x in vacuum. This means that the path difference delta x in a medium of refractive index n is equal to a path difference of n delta x in vacuum. The quantity n delta x is known as the optical path of the light. Since the optical path of rays converging at any point on the screen is the same for all the rays, the lens do not create any extra path difference in a parallel beam. Let us now compare the diffraction fringes due to a single slit with the interference fringes formed in the double slit experiment. We observe alternate bright and dark fringes in both the interference and the diffraction experiments. The fringes in case of the interference experiment are due to superposition of waves from two sources, whereas the diffraction pattern is a superposition of waves originating from each of the point sources on the single slit. The interference pattern has a number of equally spaced bright and dark bands, but the diffraction pattern has a wider central bright maximum. The intensity of the successive maxima decreases as we move away from the central maxima on either side. In the case of diffraction, the first minima is formed at an angle theta equal to plus or minus lambda by a, whereas the condition of angular separation theta equal to plus or minus lambda by a corresponds to the central maxima for two-slit interference pattern with a equal to the separation between the slits. Now, observe the intensities of the fringes formed in the single-slit diffraction and the double-slit interference experiments. When observed closely, double-slit interference experiments, we see a decrease in the intensity of the bright fringes as we move towards either side of the central maxima. This happens because of the diffraction of light from each of the single slits. In fact, the pattern is a superposition of a double-slit interference pattern and a single-slit diffraction from each slit. The combined effects of diffraction and interference are as shown. The diffraction pattern acts as an envelope and controls the regularly spaced interference pattern. The number of interference fringes occurring in the broad diffraction peak depends on the ratio d by a, where d is the slit separation and a is the width of each slit. As the value of a decreases, the diffraction pattern becomes flat and we observe a normal interference pattern.